So here's, okay, perfect. I guess I can start. All right, so okay, so what about exponential equations? Okay, so I'm gonna do basically, let's say 2 examples, guys, exponential equations. So first example, so example 1. So I'm gonna show you how to solve exponential equations in general. So example 1. So let's say you have 5 to the power 2x minus 1 equals to 5 to the power minus, say, 3x plus 4, right? So this is an exponential equation because both sides we have exponential functions, right? So this is, you see this, for example, this left side, this is an exponential function because you have some constant to some power involving x. Okay, so both of them are exponential functions because they are of the form some constant a to the power x. Well, it's not exactly power x here, of course. It's a 2x minus 1, like in the left side, that'll be 2x minus 1. But, sorry. But, the exponent, in the exponent, you have x, right? The exponent involves x, right? So if you have some constant to some power involving x, that will be an exponential function. So this is an exponential function with base. So the base is 5 on both sides. Here's your base, the constant a. It's 5. So with the same base, right? So both sides, they have the same base. Okay, this is really important. So because you will see in next example, we're gonna have exponential functions with different bases. Okay, but in this example, we have the same base, which is 5. Right, a is equal to 5. Okay, so when we have an exponential equation with the same base, all right, so then the first step would be to apply a log. So how do we solve such equation? Well, the idea is actually to apply the log in the same base. Okay, so base is 5. So what I'm gonna do, I'm gonna apply log in base 5 to the left side and log in base 5 to the right side. Okay, so in the I'm gonna probably zoom out. It's better if I zoom out. Oops. All right. Okay, so left side we have 5 to the power 2x minus 1. The right side we have 5 to the power minus 3x plus 4. Right, this is a 5, of course. So it's 5 to the power minus 3x plus 4. So the thing, guys, is that, so why do we apply log? Because when you apply log to some number with some power within or an exponent, then actually you can bring down the power in front of the log. So you see, the thing is, when you have a log 5 to the power 2x minus 1, then this power 2x minus 1, you can bring it down here in the front of the log, and the same for this power here. You can bring it down here in the front of the log, right? This is because this is one of the main properties of the log. So remember, when you have like log in some base a, it doesn't really matter base, of x to the power y, then actually you can bring down this power to the front of the log. So this is actually y times log in base a of x. Okay, so if you have some exponent inside the log, you can always put the exponent in front of the log. Okay, so once you put this exponent in, sorry, once you put this exponent in front of the log, then you're gonna have 2x minus 1 times, and then, well, there's this log on base 5 of 5, right? And the same right side, so we have minus 3x plus 4 log in base 5 of 5. Okay. Now, the thing is, this log in base 5 of 5 is actually equal to 1. Okay, that's because log in base a of a is equal to 1. So for any a, log in base a of a is equal to 1, right? So what I'm saying is that this log in base 5 of 5, that's actually equal to 1, and the same for this log in base 5 of 5, it's also equal to 1. All right, so then you're gonna have, you're gonna have 2x minus 1 times 1 equal to minus 3x plus 4 times 1. Okay, and of course, when you multiply by 1, you're gonna have just the same thing, right? It's just 2x minus 1 equals to minus 3x plus 4. Okay, so what we can observe here, guys, is that, 2x minus 1, that's exactly the exponent of left side, and minus 3x plus 4, that's the exponent of the right side. So, what we are saying here makes sense, because, so we have this 5 to the power 2x minus 1 on the left, and 5 to the power minus 3x plus 4. So what we are saying is that if you have an exponential, an equation with exponential functions with the same base, then the powers, the exponent, they have to be equal. Okay, so these two exponents, they have to be equal. But you have to be careful, guys. You need the same base, right? Because here it's base 5, here it's same base 5. So what we are saying is that if we do have the same base, then the exponents are equal. Okay, and that's exactly what we are saying here, right? The 2x minus 1 is equal to the minus 3x plus 4. Okay, so the exponents, so the exponents are equal. So the exponents here, the exponents are equal. But of course, this is under the condition that we have the same base, right? So we're gonna see in the next example when you have an exponential equation, but you don't have the same base. You have two exponential functions with different base, okay? So in this case, when you have the same base, then all we are saying here is that the exponent, they're gonna be equal. And so now I can just solve for x. That's not here. It's not very hard. This is plus dx here, plus dx both sides. So that would be 5x minus 1. Dx minus dx plus dx cancel out. So it's just 4 on the right side. There's plus 1 here, plus 1 here. So that will be 5x equals to 5. Divide by 5 both sides. And so your x is equal to 1. All right. Okay, so that's the answer, and that's actually the fine answer. There are no conditions here to check, guys. Remember, for logarithmic functions, we had to check, that your x is positive, right? But for exponential functions, your x can be any real number. So there are no conditions here to check. There's no there are no restrictions on x. So your x can be any real number. Okay, so For exponential, so this x here, it can be any real number, so there are no restrictions. Okay, so here, conclusion. Okay, so remark. So in exponential functions, x can be any real number. In exponential functions, and again, this is different from the when we have a logarithmic equation. Remember, in logarithmic equation, there is a last step where you have to check the positivity of your the solution, right? So in exponential functions, there are no restrictions or conditions on x. I mean, x can be any real number. So find answer x is equal to 1, right? So the find answer is x equal to 1. Okay, so we are done. All right, so this is an example where we do have the same base, right? Now, what happens? So how do we solve an exponential equation when we have different bases? So this is so my example number 2. So in this example number 2, let's say we have 4 to the power 2x minus 1 equals to, let's say, 3 to the power minus x plus, let's say, plus 5. All right. So this is an exponential equation because, again, we have exponential functions. This is an exponential function because you have a constant to some power involving x. And here is the same. This is an exponential function because you have some constant, which is 3, to some power involving x, right? So both are exponential functions, but then this is exponential in base 4. This is exponential function in base 4, right? And this one, of course, it's an exponential in base exponential function, exponential in base 3, right? So in this case, we have two different bases. So then the first step to solve such an equation would be, so step 1 is to apply the most common log to both sides. So I'm going to apply natural log. So we need to apply, so when we have different bases, we apply natural log, so ln. Okay, so natural log, this is, just to remind you, natural log, that's a log in base e. Remember, guys, we discussed about this special number e, which is 2.71 something, right? And we said we call log in base e natural log. So this ln, this is ln, right? This is ln. So this is what I call natural log. So this is my natural log. It's natural because in physics, it's a very natural log. Okay, so this is a natural log, and so we apply this natural log both sides. So here's my natural log on the left side, and here's my natural log on the right side. In the left side, I do have this 4 to the power 2x minus 1. And on the right side, I do have 3 to the power minus x plus 5. All right. And of course, next step, it's always the same. So once you apply a log, well, it doesn't matter in which base. So when you apply a log in any base, you can always bring down the power. So this power here, this 2x minus 1 to the front here. All right. And the same. And the same for this minus x plus 5. Okay, so that will be 2x minus 1 times a natural log of 4 equals to minus x plus 5. Don't forget the parentheses, guys. So it's parentheses minus x plus 5 times natural log of 3. Okay. Now, don't be scared of this natural log of, this natural log of 4 or natural log of 3. Okay, they are just numbers. They're just decimals, right? So, I mean, if you have the calculator, you can compute the natural log of 4. There'll be some, I'm not sure, probably 2 point something. I'm not sure. Anyway, so natural log of 4, it's some decimal, right? It's just some number, okay? So instead of replacing this natural log of 4 by a decimal, I'm gonna just keep it, right? So don't be scared of this natural log of 4. The same here for natural log of 3. It's just some decimal, right? And instead of using the decimal, I'm gonna just keep the natural log of 3. Okay, so think of the natural log of 4 and natural log of 3 as some decimals, right? Just numbers. They're just numbers, all right? Because the difference in the previous example, we had this log in base 5 of 5, but we do know exactly the value of log in base 5 of 5. We said it's 1, right? Now it's exactly 1, right? But here we have this natural log of 4 and this natural log of 3, and they are just decimals, right? So they are not exact whole numbers, okay? They are not whole numbers, they are just the decimals, okay? So this is a decimal, just some decimal. There's some decimal number, and the same here, some decimal number, okay? Now, so I'm gonna keep the natural log of 4 and the natural log of 3, and I'm gonna expand the left side. So I'm gonna just multiply. So this is 2x times this decimal, and then there's this 1 here times this decimal, right? So it's it's 2x times this natural log of 4 minus 1 times this natural log of 4. The same on the right side. So we have this minus x times natural log of 3, and then this 5 times natural log of 3. So it's minus x times natural log of 3 plus 5 times natural log of 3. All right. Now, I'm gonna write this. So I'm gonna first start. So we have 2x times natural log of 4. So I'm gonna, I'm gonna start with the numbers. So we have 2 times natural log of 4 times x. Okay. So you always keep the x last in the last position, right? So it's 2 times natural log of 4 times x. Minus 1 times natural log of 4, it's just 1 times any number would be the same number. So it's natural log of 4. And then there's this minus x times natural log of 3. And as I said, it's better to keep the x in the last position. So it's minus natural log of 3 and then times x. So again, guys, this natural log of 3, it's just some number. It's 1 point wherever, so times x. Okay, and the same for this natural log of 4. It's just some number, right? And then there's this 5 times this natural log of 3. All right, so I want to solve for x, of course, right? So the idea would be to move all the x's on one side, so then I can factor out x, and then everything else to the right side. Okay, so all the x's on the left side, everything else to the right side. So there's this x in here on the right side, so I want to move to the left side. So there's this minus natural log of 3 times x, so I'm gonna add plus natural log of 3 times x. All right, and of course I have to do the same thing on the other side, right? So it's plus natural log of 3 times x. All right, so this is, so on the left side, we do have, this is 2 times natural log of 4 times x plus this natural log of phi, which is some number, times x. And then there's this minus natural log of 4. So here's my natural log of 4 equals. So the right side, here this cancel out. And then there is this plus 5 natural log of phi, right? This is plus 5 natural log of phi. So here's my, so e equals to 5 times natural log of phi. Right? Now, as I said, you keep the x on the same side. So my x is there on the same side. Here's my x, here's the left side. Now, everything else, which doesn't involve x, I have to move to the other side. So I'm going to have to move this natural log of 4 to the right side. So I'm going to add plus natural log of 4 and do the same thing, of course, on the right side. So that's now 2 times natural log of 4 times x plus natural log of phi times x. And on the right side, we're going to have 5 natural log of 3 plus natural log of 4. Now, so the goal was to, factor out x. So now I can factor out x. On the left side, there's this, so x is a common factor. Here's an x, here's an x, so I can factor out x. So it's x times. Then what's left is, so first we have 2 natural log of 4, so 2 times natural log of 4 plus, and there's this natural log of 3, so plus natural log of 3. All right. And then on the right side, I have this 5 times this natural log of 3 plus this natural log of 4. Okay, so now I can divide by the factor, the coefficient in front of x. So this is 2 times natural log of 4 plus natural log of 3. Do the same on the right side. So it's 2 times natural log of 4 plus natural log of 3. All right, so then this thing here cancel out. So now it's just x on the left. And on the right, we have 5 natural log of 3 plus natural log of 4 over 2 natural log of 4 plus natural log of 3. Right? And that will be a fine answer, guys, because, so that's a fine answer because there are no, there are no conditions on x. X can be any real number, so so that would be a fine answer. Okay, so again, guys, I mean, if you wanna, of course, if you can try to approximate this this answer, right? You can, if you have a calculator, you can try to compute natural log of 3 and natural log of 4. So, for example, natural log of 3 is 1. Let's say 2 or 1.3 or whatever. So then you can just multiply 5 by 1 point wherever plus etc. etc. So again, just keep in mind this natural log of 3 represents some decimal, some number. And the same for natural log of 4. It's just some number, right? Is there any question, guys, about this? So this is the second example. Of course, this is more complicated than the first example because in this example, we had different bases. I mean, exponential functions with different bases, right? This is the base. On the left side, we had the base 4. On the right side, we had base 3. And so in that case, we said when we have different bases, we apply natural log. Any question, guys? Any comment? All right, so then here's an exercise. What's the 0.00, Edwin? You tried to approximate this solution? Yeah, it's probably, it's some decimal. That's why I it's better to keep this natural log of 3 and natural log of 4, right? Instead of using decimals and you can, it's better just to, keep this natural log of 3 and natural log of 4. So yeah, so here's an exercise.
Professor, I have a question.
Yes. Yeah, sure.
So you had two x's, right? And then before you divided, you had two x's. So and then you only have one when you divide it.
Yeah, but well, because I factor out x, right? Here, I guess
Oh,
you're
you
talking
factor
about,
out x. Oh,
yeah,
okay.
I guess you're talking about these two x's, right?
Yeah.
So so then your x is a common factor. So I factor out x. So if you factor out this x, then you are left with this 2 natural log of 4. So here's my 2 natural log of 4. And if you pull out this x, if you pull out this x, you are left with this natural log of 3. So here's my natural log of 3, right? And there is the plus between them. There's this plus. See this plus here? All right, here's my plus. So that's why, because I pull out the x, I factor out the x, and I got just one x.
Got it. Thanks.
Sure. All right. So here's an exercise, guys. Exercise. So please try to solve for x. So first example, first question. So we're gonna have exponential functions with the same base. So let's say here we have 3 to the power 3x minus 1 equals to 3 to the power minus 5x. Let's say plus 15, right? Number 2. So number 2, we're gonna have exponential with different bases. So let's say here's this is 4 to the power, let's say 2x minus 1 equals to let's say this is 7 to the power minus x. And here, let's say we have plus 8. All right. Okay, guys, let's say you have 10 minutes to think about this exercise. All right. If you have any question, just let me know. All right. So actually, if you have a calculator, guys, you can. So for example, natural log of 4, that would be 1.3862, etc., etc. And natural log of 3, if you try to use your calculator, then natural log of 3 would be like 1.0986, etc., etc. Kwame, you're saying you're saying 2 for number 1. Let me see. 2. Nope. Wait. 2. Oh, yes. Yeah, absolutely correct. Very good. Yeah, Kwame, Samir, you're correct, guys. Number two, guys, just be careful. This is a minus, right? This is minus x. This minus x, okay? Just be careful of the minus. Am I recording the session? I forgot. Oh, yes. Okay. So, so tomorrow, guys, you will get your homework grades and the review sheet for the second test. Kwame, you're saying yes. I think your answer is correct, Kwame. Yes. Yes, I think it's correct. I mean, I don't have the answer. I mean, I have to solve the problem, but I think you're correct. It's a lot, yeah, I know, but that's how it works. I mean, that's how it is. I mean, there's no other way. Yes, I know, I know. Um, all right, guys. I guess you are done. Well, so I hope you are done with this exercise. So anyway, so for number one, because we do have the same base, so we said the idea would be just, I mean, you apply a log in base 3 both sides, but then you end up with the exponent being equal. So for number one, you're gonna have 3x minus 1 equals to minus 5x plus 15. Okay, so this is because we have the same base, which is 3, right? There's the exponential in base 3 and exponential in base 3, right? So then the exponent, they're going to be equal. So then, so let me just write it again here. So minus 5x plus 15. This is plus 5x, 5x. So that's 8x minus 1, 15. This is plus 1, and then so that's 8x equals to 16 over 8, both sides. And as you said, guys, the solution would be x equal to 2, right? And again, there are no conditions on x, so there's nothing to check here. The x equal to 2 is your final answer. For number two, well, number two, it's more complicated because, of course, we have different bases. I mean, so this is a 4 to the power 2x minus 1. So 4 to the power 2x minus 1 equals 7 to the power minus x plus 8. This is minus x plus 8. So as I said, in this case, so we do have different bases, So then we have to apply natural log to both sides. So here's my natural log, and equal to, and here's my natural log. So then this is 4 to the power 2x minus 1, and this is 7 to the power minus x plus 8. You bring down this power here to the front of natural log, the same here to the front. And so that's 2x minus 1 times natural log of 4. And on the right side, it's minus x plus 8 times natural log of 7. All right, so now we said first you distribute. So this is 2x times this natural log of 4, and then 1 here times this natural log of 4. Same here, minus x times this natural log of 7, and then 8 times this natural log of 7. So it's 2x times natural log of 4, which is 1.3 something, minus 1 times natural log of 4. On the right side, it's minus x times natural log of 7 plus 8 times natural log of 7. So as I said, it's better to keep the x in the last position. So it's 2 times natural log of 4 times x. Okay, so when you have a product, just move the x to the last position, right? Minus 1 times natural log of 4. So this is going to be just small natural log of 4. The right side, it's minus, there's this natural log of 7, and I'm going to just move the x in the last position. Plus 8 natural log of 7. Now, the idea, guys, we said we have to move all the x's on one side and everything else to the right side. So this is minus natural log of 7 times x. I'm going to move it to the to the left side, and then there's this natural log of 4. There's no x in here. All right, that's just natural log of 4. I'm going to move it to the right side. So first, let's start with this minus natural log of 7 times x. So I'm going to add, so plus natural log of 7 times x plus natural log of 7 times x. So here, this thing here to cancel out, of course. On the left side, so we're going to have 2 times natural log of 4 times x plus this natural log of 7 times x, and then there's this minus natural log of 4, right? And the right side, we have this, 8 times natural log of 7. Now, as I said, everything, we move the x's left side and everything else to the right side. There's this minus natural log of 4. I have to move to the right side, so we're going to have plus natural log of 4 plus natural log of 4. And so now I'm going to have 2 times natural log of 4x plus natural log of 7 times x equals 2. So this natural log of 4 cancel out here on the left side. And on the right side, that will be 8 natural log of 7 plus natural log of 4. All right, so now I can factor out my x because now x is going to be a common factor in the left side. There's an x in here, there's an x in here. So I can just pull out the x, right? So x times, you pull out the x. First, there's this 2 times natural log of 4, right? This 2 times natural log of 4. Then there's a plus, so here's my plus, and then you are left with this natural log of 7, right? And then the right side is just the same. Okay, and now I can get my x by dividing by this, this 2 natural log of 4 plus natural log of 7. And you have to do, of course, the same thing to the right side. Wherever you do on the one side, you do the same, exactly the same on the other side. 2 natural log of 4 plus natural log of 7. And so this thing here cancel out, and so your x would be equal to 8 times natural log of 7 plus, then there's this natural log of 4 over, and then there's this 2 times natural log of 4 plus natural log of 7. And of course, that will be a fine answer. There are no conditions to check, so that's our solution, right? Any question, guys? So you don't have to approximate your solution, okay? So you don't have to use a calculator to compute the natural log of 7 or natural log of 4, okay? So this is, you don't have to use a calculator, okay? And so this would be a fine answer. Any question, guys? So yeah, so actually we are done with this exponential equations. As I said, last week we did different examples of logarithmic equations. So so then we are done with this chapter 3. So this chapter 3, it's included in the test. Okay, so as I said, you're gonna have a homework this week, and in the homework you have to solve exponential and logarithmic equations. All right, so I guess I can start. We can move to the next chapter. So this next chapter, chapter 4, it's not included in the test, okay? But it's gonna be in the final, okay? So this is chapter 4. Okay, so this is not included in the test, okay? But it's gonna be in the final, of course. All right, so of course it's about trigonometric trig functions, right? Trigonometric functions. All right, so before introducing the trig functions, I'm gonna first talk about the angles. How do we measure angles? We can, of course, we can use degrees or radians. So I'm going to explain the relation between degrees and radians, etc., etc., and then I'm going to introduce the trig functions. All right. So first, I guess I'm going to start with the definition of an angle. So what's an angle? Okay. Well, an angle, it's just it's formed by two rays. Okay, and they have the two rays. They have a common vertex. Okay, so this is let me write down here for you definition. So an angle is formed by two rays. Okay, that have a common a vertex or endpoint, that have a common vertex. Okay, so let's say this is here's your vertex, guys. All right, and you have a first ray. So this is here. You have this first ray. Okay, so the first ray is called the initial side. So this is my initial, let's say my initial side. Okay, and then there's the second ray. So there's the second side, this one here, and let's call the second side the terminal side. Okay, and now when you go from the initial side to the terminal side, you get your angle theta. Okay, so then when you go from your initial side to the terminal side, that'll be your angle. That'll be what I call the angle theta, right? Again, so an angle is formed by two sides. There's an initial side, terminal side. You go from the initial to the terminal, and that will be your angle theta, right? There are two different possible. There are two possible rotations, guys. So you can have a clockwise rotation or a counterclockwise rotation, right? So there are two possible rotations. Okay, so there's a counterclockwise rotation, right? So so when you so let's say, for example, so here, like this is my initial side, this is my terminal side. Okay, and so in this case, if you go from the initial to the terminal side, you have a counterclockwise rotation, right? This is counterclockwise. Okay, now this angle theta in this case would be positive. Okay, so in this case, we get positive angle. So the angle theta is positive. So when we have a counterclockwise rotation, then the angle is positive. And if you have a clockwise rotation, then your angle theta is going to be negative. Okay, so you have to keep in mind, guys, this is very important, of course. An angle, it could be positive or negative. I mean, it depends on your how you rotate, right? So it's let's say now, this is your initial side, all right, and this one is the terminal one. Of course, you go from the initial to the terminal. From the initial to the terminal, there'll be your angle theta, and in this case, you have a clockwise rotation, right? And so in this case, your angle theta is negative. Okay, Anyway, any question, guys? I mean, please feel free to interrupt me if you have any question. All right. So now next, what we're gonna do next? We're gonna try to measure the angles, right? So there are two different units you can use to measure angles. You can use degrees or radians. Okay. So um, okay. Well, before, yeah. Well, okay. Let me just talk about this degrees and the radians. So now we're gonna measure. So we can use degrees or radians, right? So for example, so let's say this is your initial side. Okay, so if you go to this terminal side, so then you're gonna have you're gonna get this angle. This is, of course, this is a right angle, and that will be 90 degrees. Yes, absolutely, Glenn. So this is 90 degrees. Okay, that's a right angle. Okay, now if you go from your initial side to the opposite side, so if you go from let's say from from this initial side to this terminal side, so you go to the opposite side, right? So that would be 180. Absolutely, Glenn, thank you. 180, right? Now if you go down to this side, so you start from this your initial side and you go all the way to this blue side. All right, so that will be well, 90, 180, not exactly 260, Glenn. It's actually 270, right? Because 180, this is 270 because that's 180 plus 90, right? And then if you have a full you have a full rotation. If you go, that would be 360. Yeah, absolutely, Glenn. So if you go from this initial side and you do like a full rotation, so in this case, so you start from the initial side and the terminal side that would one side, right? So that would be 360. All right, and all of them are positive, right? Because it's a counterclockwise rotation, right? Anyway, so this is just examples. Also, there's also this trivial example. So if you have, so when your initial side, so let's say this is your initial side, and then let's say your terminal side is actually the same as the initial side, right? This is also your terminal side. Okay, then you get the zero angle. Okay, so this is a 0 degree. This is a 0 degree. That's the zero angle. Okay. I mean, so if you don't have any rotation, if you don't move, right? If your initial side is the same as your terminal side and you don't move, you don't do any rotation, then that will be the zero angle. Okay. Anyway, so this is just some examples of well-known angles in degrees, right? Now the thing is, the question now, of course, how do we convert degrees to radians? And well, first, what's the relation between degrees and radians? So first, relation between degrees and radians. Well, the main relation is that 180 degrees, so 180 degrees, right, is equal to pi radian. Okay. Pi is a very special number. You know, it's actually equal, I think, 3.1415, etc. Yes, Glenn, absolutely. But so this is pi is a very special number. And so this is 180. So here we are using degrees, right? And here this is we are using radians. Okay. Now, how do we convert degrees to let's say to radians? Okay. So question. So how do we convert degrees to radians? Well, we have to multiply by pi over 180. So we have to multiply. So we'll multiply by pi over 180. Okay. So for example, let's say you want to convert degrees. So let's say you have 240 degrees. You want to convert 240 degrees to radians. Okay. So you take your 240 degrees, and as I said, we have to multiply by pi over 180. So it's times pi over 180. All right. So that's actually 240 over 180 times pi. Now, guys, what's really important, you have to reduce the fraction, the 240 over 180. Okay. So, for example, 240 over 180, you can, for example, divide both the top and the bottom by 10. All right. So then that will be 24 over 18 pi. So you have to keep reducing the fraction. Okay. So if you can reduce your fraction, then you have to reduce it. Right. So this is 24 over 18. You can divide, let's say, the top and the bottom by 6. So here's my over 6. So 24 over 6, that will be 4. And 18 over 6, that's 3 pi. Okay. Now 4 over 3, it's not, you cannot really reduce this fraction, right? 4 over 3, that will be actually the answer. So what we are saying here is that, so the answer is that 240 degrees is equal to 4 pi over 3. So again, guys, you have to keep reducing the fraction until you cannot. Okay, so you have to keep reducing the fraction. Okay, until the top and the bottom, they won't have any common any common factor. Okay. So that's how we convert degrees to radians by multiplying by this pi over 180. Now the other way, of course, to convert radians to to degrees. So we have to multiply by 180 over pi. Okay, so for example, let's say you want to convert, let's say you want to convert 5 pi over 4 radians to degrees. Okay, so so that's 5 pi over 4 times, we said we have to multiply. Now from radians to degrees, we have to multiply by 180 over pi. So here's my 180 over pi. There's a pi in the top, there's a pi in the, there's a pi in the top and pi in the bottom, so they cancel out. Now you have to multiply and divide. So it's 5 times 180 over 4. So 5 times 180, that's 900. 900 over 4. Now 900 over 4. So we have to, we have to divide 900 by 4. So that will be equal to 225. Thank you, Glenn. Yeah, absolutely. It's 225. So it's 225 degrees. So the answer is that your 5 pi over 4, it's 225 degrees. Okay, so that's how we convert the radians to degrees, right? So just be careful. So I mean, degrees to radians, you multiply by pi over 180. Radians to degrees, it's 180 over pi. Okay, I know it's you can get easily confused, but that's how it works, right? So then, okay, so here's an exercise, very small exercise. So you need to convert. So please try to convert. I'm gonna just zoom out. All right. So so let's say first. So please convert. So we start with the degrees. So 210 degrees to radians. Right, and then convert. So please try to convert 7 pi over 6 to degrees. All right. Okay, guys, you have, let's say, 5 minutes to think about this exercise. I think there's a storm today, right? Anyway, I hope I wouldn't have any problem with internet. Yeah, it's windy. Yeah, absolutely, Kwame. Yeah, and it's raining a lot. Yeah, again, guys, this is not included in the test. All right. Kwame, 7 pi over 6 for number 1. Yes, yes, absolutely. That's good. Correct. Yeah, so then number 2, absolutely, and then number 2 will be 210. Yeah. So yes, absolutely. So number 1, guys. So for number 1, this is a 210. Oops. So to convert, so it's 210 degrees, right? So to convert from degrees to radians, we said we multiply by pi over 180. So this is like 210 over 180 pi. And then we said we have to reduce the fraction. That's really important. Otherwise, your answer is not correct. So this is, you can divide by 10. Here is by 10. So then it's 21 over 18 times pi. We can still divide by 3. So here's over 3. Here's over 3. And so that would be 7 over 6 pi. All right, so that's, and of course 7 and 6, they don't have common factor, so then I cannot reduce this 7 over 6, so that's the final answer. So this is so this 210 degrees is actually 7 pi over 6. All right, number 2. It's 7 pi over 6. And so we said this is radians, 7 pi over 6 radians, 2 degrees. We have to multiply by 180 over pi. Right, so then pi would cancel out. So that's 7 times 180 over 6. So 7 times 180, that's 1260 over 6, and that will be equal to actually 210 degrees. All right, so then the answer, of course, is the same as number 1 actually. So the 7 pi over 6, it's just 210 degrees. All right, any question, guys? Nope. Okay, perfect. So that's how we that's the relation between degrees and radians, and that's how we measure. So as I said, there are 2 different units you can use to measure angles. So we can use either the degrees or the radians. All right. So then, okay. So then let me introduce now the trig functions. I'm gonna use.
Hi, Professor. Can you go back real quick?
Sure.
I'm still trying to
Sure.
see the converting the radian to the degree in the last one.
Yeah, sure. Oops. Is it okay here?
Yes, thank you.
Okay, sure.
This one, it doesn't really seem that difficult.
Yeah, I mean, it's not difficult to convert from degrees to radians or radians to degrees.
Okay.
Yeah, it's not difficult.
Okay, thank you. That was all.
Okay, no problem. All right. Yeah, I was saying I'm gonna now introduce the trig functions, right? So I'm gonna talk a little bit about trig functions. All right, so I'm gonna draw like a big circle, the unit circle. So here, guys, I have my x-axis, of course, and this is my x-axis, and of course, this is supposed to be my y-axis. All right, and then I have this. Here's one. Okay, it's not the line here is not straight, but it's not a problem. Here's one. This is supposed to be 1, 2, 3, 4. 1, 2, 3, 4. So this is supposed to be -1, 4. So here's -1. Okay, and I have my unit circle. So I'm gonna have this. So when I say unit circle, it means the circle of radius 1. So here's my unit circle. It's not a very nice circle, but anyway. So this is a unit circle because the radius is equal to 1. So what do I mean by the radius? So yeah, yeah, Glenn, we're gonna have a lot of triangles now. Yes. So this is a unit circle. So units. Okay, sorry. So unit circle. So which means a circle of radius 1. So if you go from the origin, radius 1, right? So if you go from from the origin to any point of the circle, like here, then this is the distance. This is a yellow segment, right? The length of this yellow segment is equal to 1, right? This is equal to 1, okay? So the unit circle, that's a circle of radius 1, which means that if you go from the origin to any point of the circle, then that will be equal to 1, okay? Anyway, so yeah, that's my unit circle. Now what I'm gonna do, guys, I'm gonna take an angle. So here's, let's say this is my initial, this is supposed to be my initial side. Cheyenne, sorry, I don't have them aligned when you look them up. Oh yeah, that's true. That's true. That's true. That's true, Cheyenne. Yeah, I can. Yeah, I can. Yeah, but I have to practice, I guess. But anyway, it's not a problem. I mean, it's fine. So I'm gonna take this initial side. This one here. This is my initial side, right? And let's say here's my somewhere here. Let's say that will be my terminal side. Okay, so this is my terminal side. All right. So of course, if you go from the initial side to the terminal side, you get your angle theta, right? So so here from my initial side to the terminal side, that will be my angle. That will be my angle theta, right? Now I'm gonna put this point here, the end point of the terminal side, I'm gonna call this is this point here. So this is the point, of course, the x coordinate of that point. So here's my x. So here's my x, and the y. This is here's my y coordinate. So here's my y. So this is the point with coordinates xy. Okay. So you see here in this picture, guys, we have like a right triangle. So there's this right triangle here. This the green one. Okay, and here's your right angle here. This is a right angle, right? That's 90 degrees. So now the sides of this triangle. So the terminal side, that will be your, that's the hypotenuse of your triangle, right? So let me draw again this triangle. So here's your triangle. You have this This is your triangle. You have this right angle here. All right. Now, the terminal side, this is actually your hypotenuse. This is my hypotenuse. That's my terminal side. My angle theta. So where's my angle theta? Well, here's my angle theta. All right, this is my angle theta right here. Okay. Now, this is my angle theta. Now, what's the opposite side of the angle theta? Well, the opposite side of the angle theta would be this side, right? This one here. This is, so this is the opposite side to the angle theta. Opposite side to the angle theta, right? Now, the adjacent side to the angle theta would be, so let me pick the blue for the adjacent side. So this side here, this one here, this is my adjacent side to the angle theta. Okay, and of course, you have your the hypotenuse. Now, what will be the length of the hypotenuse, guys? You know, the hypotenuse, that's supposed to be my terminal. The hypotenuse, right? That's my here's my hypotenuse, right? That's my terminal side. What's the length of this hypotenuse or the terminal side? Well, you know, this is a unit circle, right? So we said if you go from the origin to a point of the circle, then that will be equal to the radius, which is 1. So my hypotenuse, this hypotenuse here, this is equal to 1, right? Because I have a unit circle. Okay. Now, what's the length of the opposite side of theta, right? So let me, so the opposite side, you know, here in this picture here, this is supposed to be the opposite side of the angle theta, right? What's the length of this opposite side? So what's the height here of this, the height of this side here? Well, that's exactly, you see, this is this point here. This is the y coordinate. That would be the height of my point here, right? So the length of this opposite side is just equal to y, right? Because you see, there are here I have this exactly the same length, right? And that's exactly y. So this is equal to y, which is the same as this side, right? So both are, they have the same length. So my opposite side is equal, the length of my opposite side is equal to y. So y is equal to my opposite side. Now, what will be the length of, let me probably zoom out here. So what will be the length now of the adjacent side? Well, the adjacent side is this side here, right? This one here, this is the adjacent side to the angle theta. And you see here, guys, it's the length of the adjacent side. You see here, this is x. This point here is supposed to be x, right? So the length of this adjacent side is just equal to x. Okay, so that's the adjacent side is equal to x. Right? Now I can probably introduce my trig functions. So by definition, sine of theta, so sine of the angle theta, here's again, here's your angle theta, right? This is one here. This is your angle theta, right? This is angle theta, right? So sine of theta, by definition, it's actually supposed to be the opposite side. So this is the definition of sine of an angle. So again, guys, here, just be careful. It's not sine times theta. This is sine of the angle theta, right? So it's not sine times theta, it's sine of the angle theta. So that's the opposite side over the hypotenuse. Okay, now the opposite side, we said it's equal to the length of the opposite side is equal to y, so it's y, and the hypotenuse, we said because it's a unit circle, the hypotenuse of my of this right triangle, the hypotenuse is equal to 1, right? That's because it's exactly the radius of my circle. So over the hypotenuse, which is equal to 1. So this is y over 1. Okay. So what I'm saying is that my sine of theta is actually equal to y over 1, so it's equal to y. Okay. Now, for cosine of theta, so cosine of theta, the definition would be the adjacent side. So this is equal to the adjacent side over the hypotenuse. And the adjacent side, we said is equal to x, right? Here, we said it's equal to x over hypotenuse. Again, it's just the radius of the unit circle. It's 1. So cosine of theta is equal to x. Okay. So again, so what I'm saying here, guys, is that if you have, so what I'm saying is that if you have a unit circle, it has to be unit. Okay. So if you have a unit circle like this one here, okay, unit circle. So this is 1 here, supposed to be 1. This is a unit circle, so radius is 1. Radius is 1, and if you take an angle theta, so radius is 1, and so if you take an angle theta, so for example, let's say you take this angle here, this is theta, okay, then and you have this point, there's this point here, this is the point of coordinate xy, right? This is here's my x and here's my y coordinate. So what I'm saying is that if you have a unit circle and you have this angle theta, then by definition, sine of the angle theta is just equal to y, and the cosine of the angle theta is actually equal to x. Okay, so so what we are saying is that sine of theta, sine of the angle theta is equal to y, and cosine of the angle theta is equal to x. Okay, so for example, if you take, let's say theta is, say for example, say theta is 45 degrees, okay? Let's say, so for example, theta is 45 degrees. That's half of 90 degrees, right? That's 90 degrees over 2, right? So, so let's say you have this unit circle. So the goal here is to find, let's say you want to find cosine of theta, or cosine of 45 degrees. Let's say you want to find cosine of 45 degrees and sine of 45 degrees. Okay, so all you have to do, guys, is that you take this unit circle. Just take this unit circle. This is a unit circle. Okay, so this is supposed to be 1 here. Here's 1. So I'm gonna take 45 degrees. That's half of 90 degrees. All right. So here's my 45 degrees. diagonal, right? Just take the diagonal. That will be my 45 degrees, right? So you go, again, you go from, this is your initial side, your x-axis, to this terminal side. That's 45 degrees. All right, so that's my theta, 45 degrees. Now, if I want to find, the cosine of theta, or cosine of 45 degrees, all I have to do is to measure the x coordinate. So you see, this is here, this is the x coordinate, right? And here's my y coordinate, okay? So all I have to do to find cosine of 45 degrees, so this is cosine of 45 degrees. This is cosine of 45 degrees. All right. Now the sine of 45 degrees would be would be equal to y, right? So so cosine of 45 degrees, that's x, and now the sine of 45 degrees, that's your y. So here's, this is this is my y coordinate, okay, and so that's the sine of 45 degrees. All right. So so you can measure your x, you can measure your y, and so for this example, when theta is 45 degrees, then cosine, of 45 degrees is going to be square root of 2 over 2, and sine of 45 degrees is going to be also equal to square root of 2 over 2. Okay. Yeah, so that's for definition of cosine and sine. So you need to think of cosine as x, as the x coordinate. So you have, again, you have this unit circle. So then your cosine is just the x coordinate, and your sine is the y coordinate. Okay. Now, of course, you can define, there's a tangent of theta. So tangent of theta, that's by definition equal to the sine of theta over cosine of theta. Okay, so in the unit circle, that will be just y over x. Okay, cotangent of theta, that will be the reciprocal of tangent, so it's just cosine of theta over sine of theta. So think of cosine again. Think of cosine as x, the sine as y. Okay, so cosine is x, and my sine is y. So it's x over y in the unit circle. There's a tangent. There's cotangent. You can also define the secant of theta. Secant of theta, that's actually 1 over cosine of theta. So that's 1 over x. And there is also cosecant of theta. And that's by definition 1 over sine of theta. Okay, so that's 1 over y. Okay. Okay, so we're gonna try to measure cosine, and we're gonna try to find the cosine and the sine of different angles. But before that, guys, let me just remark one important thing here is that you know, because you have this right triangle, this one here, right? You have this right angle here. Okay. Again, this is supposed to be x, and this is supposed to be the opposite side, supposed to be y. Now, if you apply the Pythagorean theorem to this right triangle, to this blue right triangle, this one here, right? This one. Okay. If you apply Pythagorean theorem, so let me just remind you, the Pythagorean theorem says that, so in this case, so by the Pythagorean theorem, so the first side, let's say the adjacent side, that's x, so x squared plus the opposite side, that's the square, so that's y squared equals to the hypotenuse, the square of the hypotenuse. But the hypotenuse, we are in a unit circle, so the hypotenuse is just equal to the radius. It's equal to 1, so it's equal to 1 square, which is 1, right? So if you use the Pythagorean theorem in this unit circle, you get that x squared plus y squared equals to 1. Right, and then we said we have to we think of cosine as x, right? My cosine is supposed to be x, and my sine of the angle theta, that's y. So actually, we get one of the most important trig identities is that, so cosine square, that's my x square, plus my sine square, that's my y square, equals to 1. Okay, so this is this is one of the most fundamental trig identities. So remark here, because of this Pythagorean theorem, so we have cosine square of theta plus sine square of theta is equal actually to 1. So guys, when I say cosine square of theta, it means cosine of theta times cosine of theta. Okay, so it's like saying x times x. So you're just careful. So when I say, so when I write cosine square of theta, that's cosine of theta times cosine of theta. Okay. So for example, what would be cosine square of 45 degrees? Well, that's cosine of 45 degrees times cosine of 45 degrees, right? And cosine of 45 degrees, we said it's a square root of 2 over 2. So this is equal to square root of 2 over 2 times square root of 2 over 2, right? So then square root of 2 times square root of 2, that's 2 over 4. So that will be half, okay, for example. Okay, so that's what I mean by cosine square of theta. It's cosine of theta times cosine of theta. The same thing for sine square of theta, right? Sine square of theta, that's sine of theta times sine of theta. Anyway, so special angles, yeah, so let me give you the sine and cosine of some special angles between 0 and 90 degrees, okay? So so now the question is, so what's the sine and cosine of so special angles between 0 and 90 degrees. 0 and 90 degrees. Okay, 90 degrees, that's pi over 2, right? Pi is 180 degrees, so 90 degrees is pi over 2. Now, so you need to memorize, in some sense, this table of values, guys, because this is very, we're gonna use it later in the next section. So so special angles. So we have. So here's my. So here in the first row, I have my angle theta. Second row, I have my cosine of theta. And third row, I have my sine of theta. Right, so So special angles between 0 and 90 degrees. So first we have, of course, 0 degrees or 0 radians, 0. And then we have 30 degrees. So 30 degrees, that's actually pi over 6. All right. And then we have 45 degrees. That's actually pi over 2. And then we have 60 degrees. That's pi over 3. And finally 90 degrees. And that's actually pi over 2. So then actually cosine of the angle 0. So what would be cosine of the angle 0, for example? Again, we have this, we have this unit circle. I have my, this is my, supposed to be my x-axis. This is supposed to be my y-axis. So the zero angle would be, so the initial side and the terminal side, that would coincide, right? This is, this would be my 0 angle, right? This is when the initial side and the terminal side, they coincide. So that's the 0 angle, right? So I have this, this is my point here. This is my point XY. So this is my, so this is a 0 angle. All right. And here's my XY. Okay. Now, what will be the X here for the 0 angle? What's the X? If you are at 0, the 0 angle, what will be the X here? Well, the X coordinate here is 1, right? So my X, when the angle is 0, X would be 1, and what will be Y? Well, Y is because it's just the point lies on the x-axis, right? So then the height is 0, right? Y is 0. So what we are saying, guys, is that when the angle is 0, then cosine of 0 is x, which is 1, and so then cosine of 0, the angle 0 is 1. That's my x, and sine of the angle 0. That's my y, and it's actually 0. Okay, so that's why you have to think of cosine as x, and x coordinate, and your sine as the y coordinate. So for the angle 0, x is 1, y is 0. So that's why here in this table we're gonna have, so cosine of 0 is 1, and sine of 0 is 0. Okay. Now, next, so we are trying to find the cosine and sine of some special angles, right, between 0 and 90 degrees. So for 0 degree, cosine is 0 degree is, or sorry, cosine of the angle 0 is 1, and sine of the angle 0 is just 0. Now, next, pi over 6 or 30 degrees, okay. You can do the same thing. We can have, we can have like a circle. Yes, so that will be in the radians, I think, Kwame. So for example, for 30 degrees, what we can do is you can, take again unit circle. This is supposed to be your initial side, and your terminal side, it's somewhere here, and this is supposed to be your 30 degrees. Okay, this is your pi over 6 or 30 degrees. All right, so all you have to do, guys, to find the x, to find the sine, cosine, and sorry, yeah, it's 350. All right, so you know what, I'm gonna probably stop here because I have to explain how to get this cosine and sine of the 30 degrees, etc. So I'm gonna stop here, guys, and I will continue with this table next time. I'm gonna show you how to find this this cosine and the sine of these special angles next time. And then, of course, I'm gonna talk a little bit more about this cosine and sine functions. All right. So let's stop here. I'm sorry. And I will see you on Wednesday. All right. Thank you, everyone. And as I promised, I will post the review sheet tomorrow on Blackboard. Okay. Thank you, everyone. I will see you on Wednesday. Take care and stay safe, of course.